Hello everyone. The title of our project is Visual Slam using RGB-D for UGVs for indoor environments. The team members in this project are Harish Karunakaran, Gopeshh Raj, and Harshil Patel. So, the key idea of our project will be implementing the visual simultaneous localization and mapping system. The applications of such a system range from assisting visually impaired people in indoor environments to surveillance and rescue operations, and also in the online map building and localization application. So, what we have planned to use the unmanned ground vehicle for testing out our visual SLAM system. We have chosen UGVs because of their more practicality in indoor scenarios, as well as its higher time of operation compared to UAVs. So we will be using an RGB-D camera for implementing the SLAM visual SLAM, since because of its lightweight, small and cheap nature. Why is this a key research problem? One of the big factors contributing to this is the lack of a robust open source package for visual SLAM as it exists for other SLAM techniques. So, a key part of our project will be to develop an open source package for UGVs, such as the Turtlebot and the ClearPath Husky robot. Some of the previous research involved in visual SLAM have been done by Andrew Davison, where he performed real-time processing for SLAM via active tracking of landmarks. And another work by Lemar, where he used a vision-based SLAM using stereo and monocular approaches. So our approach varies from their approaches since we are using an RGB-D camera for real-time tracking of landmarks. So the technical complexities that will be involved in our problem will be it's because of its indoor nature, we'll have to encounter dynamic work environments, and we need to integrate multiple sensors such as the data from the IMU, the cameras, and combine them together. And it is almost impossible to get a perfectly online system because of bandwidth constraints. So we would have to So the approach we'll be using for our visual SLAM algorithm can be divided into three layers. The first layer is the image processing layer, where the first part we will be extracting features from an image. This will be this can be done using SIFT, SURF or feature learning algorithms. What we have planned is testing all the three algorithms and selecting the best which suits our case in an indoor environment. So the next stage in the image processing layer will be feature matching, and this completes the image processing layer. The next layer is the filtering layer, where we do state estimation using predictive filters such as extended Kalman filter or particle filters. So we have decided to use the extended Kalman filter in our case, and to filter the noise. And the third layer will be the model management layer, which will handle the synchronization between the layers to achieve near real-time visual SLAM. The hardware and the software which we will use to test our algorithm is as follows. So the hardware we will be using the Turtlebot, which sits on the base is the iRobot Create, and it has a 150 degree per second single axis gyro, and also it has a 3D sensor in the form of a Microsoft Kinect. And in the software part, the computing power, it has an Intel Atom D525 dual core processor, and it has a memory of 2 GB. It also has a NVIDIA Ion discrete graphics processor as well. So, and the softwares we will be using for control, it will be ROS, OpenCV, C++, Python, MATLAB, and the Gazebo simulator. The overall schedule of our project can be divided as follows. So from the 25th of January to the February 10th, we'll be involved in background research. And from the 5th of Feb to the 15th of Feb, we will be doing the Kinect calibration and testing out the various feature extraction and validation algorithms using MATLAB. and the and after February 15th till March 15, we'll be focusing on the Slam Visual Slam algorithm implementation. And after March 15 till the end of March, we'll be focusing on setting up our simulation environment in ROS and Gazebo. And the next 2 weeks will be focused on integrating the vSlam in our simulation environment. And finally, we'll be testing our Visual Slam on the actual hardware